Hello, everyone. Good morning, good afternoon, or good evening, wherever you are right now during this around the clock, around the globe magnetics conference. My name is Martin Lonsky, and I'm from the University of Illinois at Urbana-Champaign. And first of all, I would like to thank the organizers for giving me the opportunity to present my research and in general for organizing this very nice virtual event during these exceptional times. So in this talk, I'm going to present my results on the coupled Skyrmion breathing modes in synthetic antiferromagnets. I won't really have the time to introduce magnetic skyrmions in detail, but I suppose that most of you know these objects, which are chiral magnetic textures that are topologically protected. What I want to do here is to introduce the spin eigenexcitations of magnetic skyrmions. So basically, there exist three different resonance modes, which are called breathing and gyration modes. So if you apply an AC magnetic field out of the Skyrmion plane in the gigahertz range, you will obtain something called a breathing mode, where the diameter of a Skyrmion, as you can see here, as a function of time, it will oscillate periodically. Now, if you apply the AC magnetic field in plane, you will get gyrotropic modes, which are similar to the resonance of a magnetic vortex. So in a simplified picture, you can see here that the Skyrmion is rotating around the center, either in a counterclockwise direction or in a clockwise direction. These modes have been first predicted by Mochizuki in the year 2012, and actually only a few months after this publication, the first experiments have demonstrated the existence of these resonance modes. The most common tool is probably microwave absorption spectroscopy, an example for which is shown here for this specific material, where you can see additional resonance peaks in the Skyrmion phase that don't occur in other phases and are related to the resonance modes of the Skyrmions. Another way would be to carry out optical pump probe experiments. And people are also always thinking of new approaches like TMR measurements to demonstrate these modes. Most of the work actually has been of theoretical nature. And here, many people have performed micromagnetic simulations of these eigenexcitations in different materials and different geometries and so on. So here is an example of a Skyrmion in a confined geometry for ferromagnetic nanodot. What is also very interesting is a one-dimensional Skyrmion lattice in a nanostrip, where you excite the breathing mode of the first Skyrmion here, and because of the dipolar interaction, the breathing mode will basically propagate through this nanostrip, and in this way you can transmit information in a potential device without even moving these Skyrmions around your device, but just by exploiting these eigenexcitations. So what I'm going to focus on in this talk are those breathing modes, but in a different material system where they haven't been studied so far, namely in synthetic antiferromagnets. And in these synthetic antiferromagnets, it has been demonstrated in the beginning of this year that at room temperature, a stabilization of Skyrmions is possible. This has been done by Albert Ferri's group and reported here in this Nature Materials paper. So the simplest way to realize a synthetic antiferromagnet would be to have such a trilayer here, where you have a ferromagnet, another non-magnetic layer, and another ferromagnet layer, and these two ferromagnetic layers are coupled antiferromagnetically by means of a RKKY interaction. So what we have done is also micromagnetic modeling, and for that I want to just briefly introduce how that works and which kind of energy terms are the most important here, and which ground state we observe. So as I've mentioned, we have an antiferromagnetic coupling between these two ferromagnetic layers through this RKKY interaction. The dynamics is studied by the Landau-Lifshitz-Gilbert equation, where the time evolution of the magnetization is mainly given by these two terms. Here you have the precession term with the effective magnetic field, and this is the damping term with the damping parameter alpha. As for most material systems, an interfacial Dzialushinsky-Moria interaction is very important, and we also assume a uniaxial perpendicular anisotropy along the z direction, which is also the direction where we apply DC magnetic fields and also AC magnetic fields to excite the breathing modes in this material system. So the parameters we have used while doing our simulations with OOMF are just very typical parameters for a ferromagnetic material, as you can see here. And here you can see a picture of the ground state for the case of an applied DC magnetic field, which breaks the symmetry. As a function of the interlayer coupling strength, you can see here the Skyrmion core diameter for the top layer and the bottom layer, and you can see for strong coupling, as expected, you get Skyrmions which have a almost equal diameter, and for lower coupling strengths, the diameter of the Skyrmions in the two ferromagnetic layers is different because of the importance of other micromagnetic energy terms. So now we want to take a look at the dynamics. And in most of the cases, we have used a microwave magnetic field out of plane with 100 gigahertz in order to be able to resolve all different modes that occur. So we have calculated the fast Fourier transform of the spatially average Z component of the magnetization. So this is here the power spectral density as a function of frequency. Here we have applied the AC field only in the top layer, but we get almost the same results if we apply it across all the layers. And we've plotted here for the top layer, the bottom layer, and both layers, the power spectral density. And you can see that in total, you observe 8 different resonance modes, where the exact line shape of this first mode, for example, depends on the characteristics of the AC magnetic field. Because there is some interaction between the different modes going on, as you would expect it for a coupled harmonic oscillator system, which is basically the case here because we have the two Skyrmions which are performing this breathing motion, and this is definitely coupled due to the antiferromagnetic coupling we have here between the layers. Okay, so as I said, in total we have 8 different resonance modes. So here is plotted the resonance frequency of the different modes as a function of the coupling strength. You can see that for all the cases, the resonance frequency increases, which you also would expect for classical harmonic oscillators that are coupled by a spring. For example, if you increase the spring constant, so the coupling, the resonance will get faster, or the motion will get faster for higher coupling strengths. Yeah, so regarding the physical origin of the modes, we take a look at the snapshots of the first 3 modes on the following slide here for specific coupling strength, which is relatively high. So for the first resonance mode, if we plot the Z component of the magnetization for the top and bottom layer, you can see that it is synchronized breathing motion if you look at these snapshots here. So this is the difference between the maximum here of mz compared to the ground state at 0 time. And you can see that within this ring, the Z component of the magnetization changes in phase. So we have an in phase breathing motion for the first mode and lower frequencies. At higher frequencies for the second mode, interestingly, you can see that this happens in an anti-phase fashion. So while the diameter of the upper Skyrmion is increasing, the diameter of the lower Skyrmion is decreasing. So we have an anti-phase breathing motion. And for all the higher order modes, we usually have this coupled breathing motion hybridized with the radial spin wave eigenmodes of the nanodisk, which has also been found in previous studies where researchers have only studied a single nanodisk and the breathing modes of the Skyrmion within this disk. Okay, so just to remind you, this have been the first 3 modes we have been looking at here. And now some further interesting aspects of our simulations is that the first two modes have always a very characteristic dependence on the DC magnetic field, for example. So you can see that the dependence of mode 1 and mode 2 is quite different. Also, the dependence of the saturation magnetization in the two ferromagnetic layers, you can see that it's quite different for the two resonance modes. And this actually is very interesting because this, for every synthetic antiferromagnet system, you can get a unique dynamic fingerprint of the breathing or the coupled breathing motion. And this means that if you measure this, for example, by microwave absorption spectroscopy, you can learn more about the relevant magnetic energies or magnetic parameters and interactions of the system due to this dynamic and unique fingerprint. Also very interesting is for synthetic Ferri magnets, where we have an uncompensated magnetization. That means that we have imbalanced magnetic moments in the two layers, in contrast to synthetic antiferromagnet. If this is high enough, the imbalance of the magnetic moments, we obtain some further modes which don't have this radial symmetry like the coupled breathing modes, but you can see here that they have a very specific shape, and this would definitely also be very interesting to be studied in experiments, which will definitely be done in the near future. Okay, so to conclude my talk, we've shown that there exist in-phase and anti-phase breathing modes in synthetic antiferromagnets, where we have drawn this analogy to coupled harmonic oscillators. We have shown here the systematic dependence on various magnetic parameters, which gives us a unique dynamic fingerprint. And if you're interested about the details, you can take a look at this preprint on arXiv, which has been now accepted very recently in Physical Review B. And also feel free to send me an email if you want to know more. And otherwise, I'll be happy to answer any questions now. And I would like to thank you very much for your kind attention.